Hello everyone and welcome back to another Stat 437 lecture video. In today's video, we're going to be talking about analyzing continuous longitudinal data. And in particular, what I want to talk about is what does it mean to analyze continuous longitudinal data? What are our goals with doing that? And sort of how can we naturally come to a method for doing this based on everything that we've talked about with linear regression, right? So we have this tool of linear regression, and it seems like maybe it would be well suited for this purpose, but it's not. And so we want to figure out, why can't we just use linear regression? Why is it that we need additional tools? And how can we get from linear regression to something that will work for continuous longitudinal data? Okay, so that's sort of the goal of the lecture today. Now, I'll say in advance that this is going to be the first sort of long form video that's going to be entirely new content, and so some of this might be a little bit dense. As always, if there's anything that's unclear in this video, please reach out to me and ask any questions you might have. I'm happy to clarify anything, and if there's any mistakes or clarifications or corrections that I need to make, I'll do that and I'll let you all know about that. Okay, so with that, I want to start by asking the question, how do we analyze longitudinal data? And specifically, continuous longitudinal data. But I think it's important to start with a question of, what does it even mean for us to analyze continuous longitudinal data, right? We're talking about this as the goal, but what do we really mean when we're talking about that as the goal? So I have this diagram here, and there's sort of a lot going on here, but if we take a look, these circles throughout the middle of the diagram, labeled y1, y2, and y3, represent our outcome. So again, remember that y is always the variable name we use for our outcomes. Okay, and so we're looking at longitudinal data here that have three different time point measurements. Okay, for each of the outcomes, we also have a corresponding x, right? So x characterizes our explanatory factors. So we have x1, x2, and x3, and those would correspond to measurements of explanatory variables at the time point 1, time point 2, time point 3. I also have labeled these constant baseline factors. The idea with this is that it would represent any explanatory factors which don't change over time, right? So if you have anything that's constant over the course of a study, say the treatment group that someone's in, that could be considered a constant baseline factor because it's not going to evolve. And then finally, we have this time progression, right? So the whole sort of point of longitudinal data is that time is sort of moving onwards. And so we can think about incorporating effects of time. So in this diagram, every arrow between two factors is some effect that we might care about, right? So we have these constant baseline factors, and there's arrows into the outcomes from the constant baseline factors. And so that would be the effect of a constant baseline factor on the value of our outcome. We also, of course, have effects of the explanatory factors on the outcomes. So an arrow from x1 to y1, x1 to y2, x1 to y3, and so on. And we also have arrows from the time into our outcomes. So if you remember from that introduction to longitudinal data, one of the things that we want to figure out is, what are the impacts of time on the different outcomes? Okay, so this diagram here sort of captures the way that we're going to start thinking about these relationships. And that's, we have this sequence of outcomes, and we want to figure out sort of estimating the numerical values of these arrows. We want to know, which factors actually have a positive effect or a negative effect on some outcome. And we want to try and quantify that and answer questions about that. Is it statistically significant? Do we care about it? Is it a large effect or is it a small effect? That kind of thing, right? So when we're talking about analyzing continuous longitudinal data, what we're really talking about is finding a way to mathematically represent the relationships that are depicted in this diagram. Now, while we are looking at this diagram, I'll also mention a couple of other things. So the first is that these explanatory variates that are changing over time, well, we can think about them as sort of being subsets of one another, or different factors. So let's take a concrete example and say that yi is something like blood pressure or heart rate or some factor like that. And maybe our explanatory factors are the amount that someone smokes. Okay, and so we want to know, how does smoking impact someone's blood pressure, for instance? All right, and so maybe we're, x1 is at time 0, x2 is 6 months after, and x3 is 6 months after that, right? And so if the factor that we're measuring is how much you smoke at that time, right? So how much are you smoking at the baseline time when the study started? How much were you smoking 6 months later? And how much were you smoking a year into the study? Then that would be our x1, x2, and x3. But you can think about there being these delayed effects, right? The amount that I smoke today might impact my heart rate 6 months down the line, even if I were to stop smoking right now, and so on. And so we're going to have to sort of be careful about how we think about the evolving effects of these factors over time, right? And the other thing is, oftentimes we're not going to be distinguishing these constant baseline factors from our x1, x2, x3, right? So if we have a treatment group, say, placebo versus active treatment, we could just think about x1, x2, and x3 having the exact same value of that constant baseline factor, and then drop this term, pull it out separate and include it here. And the last thing is that we're going to want to start thinking carefully about how we include time as a factor into our models here, right? So, generally we have this sense that there's this progression of time, and then the progression of time impacts our outcome somehow, but we're going to have to specify exactly how that works. And so, we'll have to be a little bit careful about that. And then just like how we might lump constant baseline factors into the x's, oftentimes in our actual data, we're going to lump time into the x's as well. And so then, it's all going to be, we have a set of x's, we have a set of y's, and we want to figure out what is the numeric relationship between those x's and those y's, and how can we explain the y's from the x's. So that's what we're actually talking about trying to do. We can write this in mathematical notation by talking about this conditional mean here, right? So we want to be able to fit a model that gives the conditional expectation of yij, given xij, the explanatory factors, and the time. And we want to do this in terms of interpretable parameters. So this interpretable parameter part matters a lot, because ultimately we're going to want to use these models to answer questions about the world. And if we don't know what the parameters mean, well, then that's not going to help us answer questions about the world, right? So this is sort of our goal stated mathematically. If it helps for you to think about it in terms of a diagram, our goal in the diagram is to put labels on all of those arrows there. Right, so that's what we're actually trying to do. Now, we can take a look at a concrete example for this. So this is the TLC data. We've seen this a couple of times already. And the idea is that there were 100 children in the study. They were all assigned either a placebo or an active treatment. So that's a P or an A. And they had, at 4 different times, the level of lead in their blood measured. So that's W0, 1, 4, and 6. Okay, so on the left-hand portion of this table here, I'm showing the first few and last few rows of the data when it's in wide format, so when each row represents a single person. Then on the right-hand side of this table here, I'm showing it in long format. So in this case, what we've done is we've pulled and expanded the data out so that each row represents an individual, and then it's one time point for that individual, right? So this would be individual 1 at time 0. It's labeled as time 1, but it's week 0, right? And so this 30.8 corresponds here. And then you would have the second row is the second individual at time 1, and so on and so forth, right? So there's a slight sort of misrepresentation of this, because the right-hand side would actually be 4 times as many rows as the left-hand side, but just for sake of getting it all on one side here. And so if we're taking a look at the right-hand side of this data, so we're taking a look at the long form, right? We have an outcome variable, which I've labeled as a W here, and that's a continuous outcome, the amount of lead in the children's blood. And then we have 2 explanatory factors. We have this treatment variable, which is either placebo or active, and we have this time variable, which is one of 4 categories, 1, 2, 3, or 4, right? And so the question is, if we want to measure or we want to model the expected value of W given the treatment and the time, how might we go about doing that? Does that look familiar? And I ask this only slightly as a rhetorical question. I'd actually encourage you to think about it. Does that look, is there a way that you would think to go about doing this? Now, given what we've been talking about in this course so far, it's sort of natural to ask, could we use linear regression? Why can't we use linear regression, right? We have a continuous outcome and we have two explanatory factors. That seems like a very natural fit for using linear regression. So what is the problem with doing this? Well, I actually went and fit this model in R using LM. All right, so I took the explanatory factors of time and treatment. I treated them both as factor variables, and I took W as our outcome, and I just fit a linear regression model here. So you can see that here we have effects for the intercept, so our beta 0 term, and then we have for time equals 2, time equals 3, or time equals 4, a different effect where time equals 1 would be the baseline. We have an effect for the treatment being placebo, and so the active treatment would be a baseline, and then I've included the interaction between all of these different terms. So it's the fully saturated model, and you can see that we get estimates for all of these different parameter values, and we get standard errors, and we can even test, are these significant at a 5% level, or whatever significance level we want, and you can see that most of the effects appear significant here. And so this model can be fit, and that feels like a very natural thing to do, right? We have a continuous outcome, we have two explanatory factors, we can fit the saturated model, we can take a look at it. And so the question for us, or the question in this course is this valid? And so to answer that question, well, I'd encourage you to think about what this is saying about our data. What are the assumptions of the linear regression model? So again, I'd encourage you to actually think through this. I will give away the answer here in a moment, but there's a few assumptions that we're making about linear regression. And so the first is that we need the conditional mean to follow a linear structure, right? So if we have the expected value of Wij, given the treatment and the time, we would need this to follow this linear structure here, where we have the intercept and then a treatment term, and then a term for time being 2, 3, or 4, and then the interaction between treatment and time equals 2, interaction between treatment and time equals 3, and the interaction between treatment and time equals 4. And so we have these 8 terms here. And implicitly, there's nothing wrong with this assumption. It might not be the most parsimonious way of modeling this, but in theory, we could actually model the mean in this way, right? There's no obvious violation of any assumption here. The next assumption that we commonly make in linear regression is that we have constant variance. Okay, so here that would mean that the variance of Wij is equal to sigma squared for all I and j. Now, this assumption might be slightly problematic, and the reason is that perhaps there's more variance at one time point than another, right, between individuals. If we were looking at the data when we were plotting it and exploring it in the first lecture, it might be the case that you'd expect to see more variance early in the study before time has sort of progressed and pushed people into a range. But again, implicitly, there's nothing wrong with this assumption. Empirically, it's something that we would want to test, but there's no reason, sort of by the nature of the data, that this would have to be invalid. And so the last assumption that we commonly make with linear regression is that the values of Wij are independent. And this is where we're going to run into issues, right? And why is it? Well, we're dealing with longitudinal data, right? And the whole sort of key point about longitudinal data is that within an individual, you have correlation, right? So we can take a look at this correlation plot here. And again, we saw this plot in the exploratory analysis, but there's correlation within the individuals. So W1 and W0 are correlated within any individual. W1 and W4 appear to be very strongly correlated within an individual, right? And so when you expand this out into wide or into long format, you're running into this issue where different rows aren't actually going to be independent if they fall within the same individual, right? So the linear model that we were just looking at is only going to work if we're willing to assume that the observations are independent. But we know, given this correlation matrix, that they can't be independent because within each individual, we see this really strong correlation between their measurements at week 0, 1, 4, and 6. Okay? And so that is fundamentally the reason that we can't use linear regression directly. That's why it's not going to work, is because we don't have independent data. All right? And so if we can't use linear regression directly because of this independence, well, what can we do? And again, I'd encourage you to start thinking a little bit about this, right? So when we're looking at our data, we have this wide format and we have this long format. And the long format looks very naturally like a linear regression. The problem is that the rows aren't actually independent of one another. Now, when we're in wide format, right, we actually do have independence on the rows, right? Because each row represents an individual, and we always assume that individual 1 is independent of individual 2, is independent of individual 3, and so on. And because of that, we have independence on the rows. Now, the problem with the wide format data is that we don't have a single outcome, right? We have W0, W1, W4, and W6, okay? So we can't use a univariate linear model here, but is there some way that we might be able to use a multivariate method, perhaps? So how might we think about doing that? Again, I'd encourage you, if you've seen sort of any multivariate analysis before, to think a little bit about how this might happen. But so when we have the data in long format, what I was just saying is that it appears as though they are univariate data, right? But when we write them out in wide format, we can see that they're actually kind of vector data, right? So we could think about defining this vector W, and this vector of W is going to have W0, W1, W4, and W6 in it. And so in this sense, when we're analyzing longitudinal data, what we are really doing is doing multivariate analysis, right? And so this multivariate analysis is what's going to account for the lack of independence between individuals, right? And so I'll take a second here and write this out somewhat more explicitly, just to make sure that we're really harping on what's happening, okay? So in our long format of data, if we just say that we do this simplified example where there's two individuals, right? So we have this ID, we're going to have individuals 1, and we have individual 2, okay? And we're going to have some outcome for them, and let's say that we measure it at time 0 and at time 1. Okay, so the most simple form of longitudinal data here, right? So then here what we're going to have is sort of individual 1 measured at time 0, individual 1 measured at time 1, individual 2 measured at time 0, individual 2 measured at time 1. Okay, and so this is the wide format. And then when we write this out in long format, and maybe what I should do here is just include a treatment indicator as well, just to give us a factor here. So let's say that individual 1 receives treatment active, individual 2 receives treatment placebo. Okay, if we extend this out into long format of data, right, we're going to end up with 4 rows in this data set. So we're going to end up with a column for Y, let's say ID, Y, and treatment. Okay, and we also want to add in a time column as well. And so we'll have individual 1 at time 0, individual 1 at time 1, individual 2 at time 0, individual 2 at time 1. So then we're looking at Y10, Y11, Y20, Y21, and we said that individual 1 was the active treatment. So that's active, active, placebo, placebo. Okay, so this is the long format. And again, this is data that looks like we could do a linear regression of Y based on treatment and time. And the problem is that Y0 and Y1 and Y10 and Y11 and Y20 and Y21 are not independent, right? So these are not independent. Okay, but if we're back up here in this wide format table, if we think about writing this out as a y here, where this is a vector of y10, y11, write that as a vector, and then we write this y20, y21 as a vector, right? Well, now we have independence between these rows, right? So those rows are actually independent now. And so if we could find some way to analyze multivariate outcomes, now we're back to dealing with these independence, okay? And so based on the way that we approach linear regression, well, one of the ways that we can do that is by looking at assuming that our data are normally distributed and then finding the MLE. And so from that, there's this natural extension. What if we assume that instead of the data being normally distributed, we assume that they are multivariate normally distributed? So what I mean here is that we're taking those vector valued outcomes, right? So we're combining all of the observations that we have for an individual, making a vector out of that, and we're saying that vector is going to be multivariate normally distributed. Its mean is going to be given by this xi beta, and we're going to say that it has some covariance matrix here. We're writing that as sigma I, and we'll talk about that in some detail later. Now here I'd point out that this xi is going to be a matrix. Again, we talked about that in notation early on, but that's going to be a matrix where each of the rows of the matrix is one of our xi observations. And so here you can see that we essentially are working from the same place that we had in the linear regression when we assume normality. The difference is our outcome is now a vector. So instead of it being univariate, it's a vector. Now, if you're unfamiliar, or if you forget, the density of the multivariate normal can be written out in explicit form here. And so using this, we could sort of take the same theoretical approach that we did with linear regression. So what theoretical approach would that be? Well, what I'm proposing is that we specify a linear form for the conditional mean of yi. So that is yi given xi is going to have mean xi beta. Here xi is a matrix and yi is a vector. So this is a multivariate expectation. Okay. We're going to account for correlations within individuals or covariance within an individual through this covariance matrix sigma I, right? So we're not going to assume that they're independent because we have this covariance between these different observations, but we are going to assume that any two individuals are independent. So individual I and individual J don't share any dependence there. And if we make those assumptions and then we assume multivariate normality, then we could theoretically find the MLE for these parameters, right? And I'm saying we could theoretically find this MLE because it's not entirely clear that this proposal makes a whole lot of sense, but we could do it, right? In the same way that if you have a univariate outcome, you can assume normality, you can assume this constant variance, and then you can find the MLE for your regression parameters. We can instead treat our outcome as multivariate, assume some covariant structure, and then find the MLE based on the data there, right? And so this is sort of the idea of these linear marginal models, is instead of assuming univariate normality, we assume multivariate normality. Now, as you can tell from what's written on the screen here, it's going to end up being slightly more complicated, right? This covariance matrix alone is going to be a little bit complicated. And so what I want to do very quickly is just remind you all what it is that we're actually talking about with a covariance matrix, right? So I'll pull this up, and then I'll also open up my ability to take some notes here and walk through this, right? But so recall that yi is going to be a vector, right? And it's a vector of all of the outcomes that we've observed for individual I. So we're going to have yi1, yi2, and I believe that on this slide I'm assuming that yi is p-dimensional. So this is going to be up to yip, right? So we have this vector here. And we can think about what we mean when we say the covariance of yi, right? So the covariance of yi we've given this name of sigma I. And there's a few ways of thinking about this, right? But the most obvious way is that this is going to be a p by p matrix, and the p is coming because it's a p-dimensional vector. It's a p by p matrix, and I have this written out down here. But on each of the diagonal entries, we're going to have the variance of yi1, and then we would have the variance of yi2. Variance of yi2, and so on. And then each of the off-diagonal terms is going to be the covariance between these terms. So the covariance between yi1 and yi2. And of course, the covariance between yi1 and yi2 is the same as the covariance between yi2 and yi1. Right, and so you can fill out this whole matrix that we have written out over here. And with this sort of full covariance matrix, what we're saying is that any two components of the vector here, of our outcome vector, any of these components, are able to be related to one another based on this covariance matrix. Now, oftentimes when I've been talking about the relationship, I haven't been talking about it as covariance, I've been talking about it as correlation. Right, and so if we have two random variables, x and y, remember that the correlation between x and y is going to be given by the covariance between x and y. And we divide that by the variance of x times by the variance of y, and then you square root that whole thing, right? And so we can rearrange that, and we find this relationship between the covariance of x and y as given by the correlation between x and y times by the square root of the variances, right? So when we're talking about accounting for correlation, you can account for covariance. It's exactly the same thing. Okay? And so if we assume that there's constant variance across time, right? So if we assume that the variance of yi1 equals the variance of yi2, and so on, up to the variance of yip, right? And we just call this sigma squared. So we have constant variance over time. All right. And if we use a shorthand for the correlation, right? So if we're taking the correlation between yij and yil, and we write that as rho of j and l, well then remember from the previous slide that we have the covariance between yij and yil is going to be equal to the correlation, so that's rho jl, times by the square root of the variance, right, the variance of yij, variance of yil, and those variances we've just assumed are both sigma squared, right, so that's rho jl times by the variance of sigma squared, and so this is going to be sigma squared rho jl, right? So that's the covariance between these two. Well, now given by this, right, if we write out this correlation matrix, if we call the correlation matrix R, so the correlation matrix is the matrix that has just all of these row terms, right, for each of the corresponding entries, then if we take sigma squared and we multiply it by that correlation matrix, then we get our variance matrix. Okay, so to clarify exactly what's happening here, we've made the assumption that there is this constant variance across all time, right? And from this constant variance assumption, if just using a little bit of simplifying notation, we can write out the covariance matrix, the sigma I for the individual, as sigma squared times by the correlation matrix. And so why is it that we're doing this? Well, if we make these assumptions and we make this multivariate normal assumption and we've correctly specified the linear style for the mean, then we can estimate the parameter value beta hat based on this closed form estimator. So this closed form estimator is going to be the maximum likelihood under the assumption of multivariate normality. And you can see it takes a similar style to what the ordinary least squares estimators are, right? So we have sort of an x transpose x inverse term and then an x transpose y, but this correlation matrix is cropping up here. But all told, this is just coming from maximizing the likelihood of this multivariate normality. And then we can also estimate the variance parameter from the same maximization, and we could also solve numerically for the correlation, right? And so these estimators, I assume you could work through the calculus to do, and in fact, we'll actually look at how we get to these answers in the theoretical video that's accompanying this. But for now, if you just take these as the closed form estimators, what we've done is we've said that we want to model the conditional expectation of our outcome given our explanatory factors. And so in order to do this, we're specifying a multivariate linear model. We're taking the concept of linear regression and we're saying, okay, but what if we just make the outcomes multivariate instead? And so to do this, we're using the multivariate normal distribution. And when we take that multivariate normal distribution, we need to specify some sort of covariance structure. And so we assume constant variance over time, and we otherwise don't make any assumptions on the variance. And we can solve for the maximum likelihood estimators, and we get this closed form expression that we could in theory use to estimate these parameters. So ignoring whether any of these are good assumptions or not, there's sort of this natural question of what comes next? Like, how do we use this? What is the point of sort of walking through this model specification? And so there's a few steps that we would want to use, assuming that this modeling is sort of good, right? The first is that we want to be able to do inference, right? So fitting a model is only as useful as it is able to answer questions of statistical significance mostly, right? And so with our linear regression, we knew that we could test the significance of any specific effect. Can we do that with this, right? That's the first question. The second is about these time trends. So again, one of the big points of longitudinal data analysis is that we can capture the effect of time on an outcome of interest. And so do these models sort of accommodate different time trends? How do we accommodate different time trends in these models? The third is, can we specify scientific questions of interest and answer them, right? So again, when we're thinking about linear regression, one of the big things that we're saying is we have an outcome, we have some factors that we might care about, and we want to answer some scientific question about how those factors impact that outcome. Can we do the same thing here? Does this work? And finally, there's that whole correlation matrix, right? So in linear regression, all you had to do was assume that there's some constant variance term. Here, we've introduced this whole sigma I deal, and what do we do with that? How do we accommodate that? How does that work? And so really the punchline of the rest of this lecture is going to be taking these ideas of marginal linear models that we've sort of discussed here and talking about how we can sort of accommodate all of these next steps, all of these questions, right? And so to sort of summarize where we're at right now, what we've done is we've shown that linear regression seemed like a natural way to try to analyze continuous longitudinal data, except there's correlation, and so we can't do univariate linear regression. However, if we keep the data in wide format and we think of our outcomes as being vectors, well, then we're back to this independent assumption that we worked with linear regression. And so from that assumption, it seemed to make sense to extend the univariate normal situation to a multivariate normal situation. And in order to do that, we have to think about the variance structure and the mean structure as a matrix times by a vector and so on. And so now we're at this point where we want to see, does this modeling approach make sense? And that's going to be what the rest of this lecture focuses on. So the first piece that we're going to talk about is inference. How do we conduct inference from these marginal linear models here? So we can show, and again, we will sort of show this piece in the theoretical video, that these maximum likelihood estimators that were presented on the previous slide, that they follow a multivariate normal distribution asymptotically. So as n gets really big, they act as though they are multivariate normal. And again, they're going to be asymptotically unbiased, right? So the mean of that multivariate normal is going to be the true parameter. And we're going to have this variance expression here where it's given by sort of, again, this expression of an x transpose x inverse multiplied by the constant variance that we've assumed here, right? And so all of these factors can be estimated by plugging in the estimates, the MLEs, from the previous slides, right? And so what this means is that asymptotically, we know the distribution of our estimators, just like we did for linear regression. And because we know this distribution in the same way that we did for linear regression, basically all of the same results that we saw for linear regression are going to hold here. And most importantly, we have the standard error estimates, right? And so from these standard error estimates, we can start deriving Wald statistics. Okay, so if you remember from sort of any of your statistics classes so far, if you have a normally distributed or an asymptotically normally distributed estimator, then you can say that if you take the standardized version of it, so the estimator minus the true value divided by its standard error, that's going to be approximately a standard normal distribution. And so, moreover, if you want to test a hypothesis of, say, beta j equals beta star, well, then, just like we would do with linear regression, if we plug beta star in for beta j here, then under the null hypothesis, where those two are equal, we're going to see that that's a standard normal. And so then we can start using those regular t-tests that we would think about, right? Or you can think about building out confidence intervals by inverting this, right? So to remind you of that, if we go, if we have our beta hat j, and we're saying that beta hat j is approximately normally distributed according to beta j with some variance term here, which we'll just call var of beta hat j, right? Well, then we can develop a, say, 95% confidence interval for beta hat by taking beta hat j plus or minus 1.96 times by the standard error of beta hat j, right? And that's going to give us a 95% confidence interval. Of course, this 1.96 is coming as the z-score of 0.975, right? So all of this should be familiar from your previous statistics courses, but the idea is that we can take this asymptotic distribution of these values and use those to develop confidence intervals, to test hypotheses, etc., in exactly the same way that we're doing for standard linear regression. And so the point there is that just like linear regression, inference actually comes fairly easy when we're dealing with these marginal linear models. So the next point after inference was thinking about time trends. So the general idea is that we can include time as a covariate in the model. Okay, and we discussed this a little bit when we were introducing notation, and we discussed the idea of data being balanced. And so balanced data occur when we've measured all individuals at the same set of time points, and sort of everyone has complete observations. And so the choice really becomes, how do we include this in the model? So if you remember back to the linear model that I fit at the beginning of this video, I included time as a factor variable in that model, right? So there was a different time effect at time 1, 4, and 6, and then the baseline time effect. And so if there's relatively few time points that we've taken measurements at, and if they're balanced, then we can do this. And the benefit to doing this is that it becomes this saturated model, right? We can accompany arbitrary patterns in our data by fitting these as factor variables. However, if the data aren't balanced, or if there's too many time points, so if we haven't measured everyone at the same set of time points, or if there's, say, 10 or 15 different times that we've measured at, then it becomes a lot harder to include it as a factor variable. And the reason is just that we start having to estimate too many different factors in the event that we've measured at very many different time points. So if you think about, again, the example where we have a binary treatment, active versus placebo, if there's 4 different points that we've measured it at, then we saw that we needed 8 parameters. But think about if instead you had, 10 or 15 different time points than you measured it at, then you're going to need, the number of time points minus 1 main effects, and then you need that many again for the interactions between that and time. And so you can see that sort of starts to get too large in the model. And if the data aren't balanced, so if we haven't measured everyone at the same time points, then it doesn't make sense to think about it as a factor, right? If you take patient 1's blood pressure at month 1 and patient 2's blood pressure is at month 2, well, if that's the first measurement you have of both of them, then they're not really at the same point in time, right? And so if that's the case, then we'd want to include time as a continuous variable, right? And if we're including it as a continuous variable, just like any other continuous variable that we would include in a model, we could think about including quadratic terms of time, right? So you could include time and time squared, or logarithmic times, or any other form of it, right? So you can think about measuring sort of the effect of log time versus the outcome, or time squared versus the outcome, or whatever might make sense in that case. You can also think about including time in sort of a more meaningful sense, right? So age becomes a very obvious example. If instead of doing time from a study where we're measuring, 0 weeks past, 1 week past, 4 weeks past, maybe it makes more sense to think about how old the person is. And so in that case, that's still a time effect, but that's a time effect with a more direct interpretation. Or same thing with, day of the week, month of the year, that sort of thing. So we can also have all of this choice about how we define time as a covariate. And it's going to depend on what we've measured and what we are interested in. So one point that's really important for this class, and I think generally speaking, it's important for advanced statistics, is that oftentimes the choices that we make are going to be dictated both by the available data, but also by what we're actually interested in, right? So if I want to know how does, aging affect someone's rate of developing dementia, probably what I actually care about is how does their age, when they turn 75, when they turn 80, when they turn 85, how does that impact the rate at which they develop dementia? I probably don't care about, 5 years after they've entered my longitudinal study, they're more likely to develop it, because 5 years after they've entered my study doesn't mean anything in the general scientific question here. So it's important to start thinking about, what are the questions that we're actually trying to answer? What data do we have that we can try to use to answer these questions? And then from there, start thinking about what is the most appropriate timescale. So again, if there's relatively few time points, it's easy. We'll just include it as a factor variable. But when there's more time points, or when the data are imbalanced, or when sort of there's more going on, we're going to need to think about it. But we can think about it the same way we think about any other covariate in this model. So again, marginal linear models, well, they can account for sort of arbitrary time trends in the data. So that's good. And that brings us to this next question of scientific questions. So generally speaking, our scientific questions in linear models are expressed in terms of hypotheses surrounding combinations of these parameters, right? So what I have here is I'm talking about taking a linear transformation of parameters of beta. But I think this is probably easier to understand if we think of an example here. So if we have our beta parameters that we've estimated beta hat, right? Now we know that each of those beta hat parameters corresponds to the effect of some variate of interest on our outcome. And so let's take this really simple example, and we'll say that our conditional mean is going to be given by beta 0. And then what we'll do is we'll just have a fairly simple time effect. And let's say that we took measurements at time equals 0, time equals 1, and time equals 2. And we're treating these as a factor variable, right? So time equals 1 may have been 6 weeks later, time equals 2 could have been a year later, whatever the case may be, right? But so the saturated model here is going to be beta 0 plus beta 1 times by the index that time equals 1 plus beta 2 times by the index that time equals 2, right? And so the idea here is that beta 0 represents some sort of baseline effect. Beta 1 is the effect of the observation at time equals 1, so it's the first time effect, and beta 2 equals the observation of time equals 2, right? And so a question of interest for us might be, is there actually a significant time effect, right? And so what would it mean if there wasn't? Well, if there wasn't, what we would be saying is that beta 1 would equal beta 2 would equal 0, right? And so you can think about this in a couple of different ways. The sort of the most concrete way for me thinking about this is thinking about it as two different hypotheses that we want to be true at the same time. So we want beta 1 equals 0, and we want beta 2 equals 0. Okay? Now, if we think about our betas as a vector, right? So we're thinking about, we have beta 0, beta 1, and beta 2, right? Now, what we could think about here is, so this is our nice little 3 by 1 vector here. If we define a matrix L, and my matrix L, I'm going to write out as 0, 1, 0, 0, 0, 1. Okay? So what am I doing here? Well, if we take L and we multiply L by beta, then what we're going to see is that this is a 2 by 3 matrix, right? And so we're going to get this 2 by 1, and you can see that this first row multiplied by beta here is just going to give us with beta 1, right? Because it's 0 plus 1 plus 0. And then the second one is just going to give us beta 2. And so in this case, this compound hypothesis that we have here of beta 1 equals 0 and beta 2 equals 0 is the same thing as saying L beta equals 0. And here 0 is actually sort of the vector of zeros, right? And so we can express this scientific hypothesis of no time effect as a hypothesis in the form L beta equals 0. Now, the reason that we care about this is because if we have these joint hypotheses, well, L beta follows a distribution that we know as well, right? And so in particular, L beta is going to follow a normal distribution, which means that we can use Wald statistics as well. And so we have this quadratic form here, and it's kind of a mess to write out, but we'll see some examples of this later on. The idea being that we can take these joint hypotheses and we can use them to sort of frame a hypothesis with a known distribution that we can then use to test. So we could test, is there a time effect based on this result here? So that's why this result is powerful. So sort of, summarizing what I was just talking about, many questions that are of scientific interest can be framed as a question of L beta equals C. So is the effect of a placebo any different from the effect of an experimental treatment? Well, here, if you take a difference, so we have a 1 corresponding to the effect where the placebo is, a -1 where the experimental treatment would be. Well, if those differences is 0, well, then L beta equals 0 is going to test that hypothesis. Is there a time trend that's going to be the same between individuals in the placebo and the control group? This is the one that we just looked at, right? Where we have a 1 in a particular column corresponding to the first time trend point, a 1 in a particular column corresponding to the next time trend point, and then testing L beta equals 0 gives us that scientific, the question of scientific interest there. We could also think about doing this as a prediction, right? So if we want to know if we have a specific set of covariates x and we want to know what is the most likely outcome for that patient, well then, if we take L equal to x, x beta is going to be a prediction, and we could build up a confidence interval, right? So a lot of the types of things that we care about that are of sort of scientific interest can be expressed in these forms of L beta. And so this is going to be our primary device for answering scientific questions, is going to be these results. Now, when I actually work through an applied data set, we'll see many different examples along these lines, and so you'll get a lot of practice with doing it. But I'd encourage you to start thinking about how can you translate a question about, say, the effect of treatment, the effect of a covariate, whatever. How can you translate that into a statement about the covariates, about the parameter estimates? And then from the parameter estimates, how can you translate that into a matrix statement, right? So just to clarify exactly what I mean, in this example that we were doing before, we had this question of, is there a time effect? So we translated that into a statement about the parameters. From the parameters, we developed this matrix L here, and then that gave us a statement of L beta equals 0, right? And so we started from scientific question, worked down to this compound hypothesis. So that's going to be this very powerful tool that we have to answer questions of scientific interest. And we'll be seeing that come up all over the place. So I'd encourage you to try and get comfortable with it. So we also have the concept of correlation, right? So up until now, we had assumed that there was constant variance across all of our observations. That might be a shortcoming because, at different time points, we might expect there to be different amounts of variance in the data, for instance. Okay. There's also a problem that it requires quite a few different correlation parameters, right? So we saw that in that matrix, that R matrix that we were talking about, we require to estimate k times k minus 1 over 2 total correlation parameters if we wanted to estimate what we were actually talking about. Now, if we're only talking about 4 different data points, right, then we can take k equals 4, and so then we're looking at 4 times 3 over 2, which is, I guess, 6 correlation parameters, right? But if k is now 10, right, I believe that's 45 different correlation parameters if we have 10 longitudinal points. And so very quickly, we're going to be estimating way more parameters than we likely have the data to actually estimate, or at least to estimate effectively, right? So that's going to be a problem. It also requires balanced data, right? So here, we're talking about the correlation between, W0 and W1 in the TLC example. Well, that's the correlation between week 0 and week 1, which required that everyone was measured at week 0 and everyone was measured at week 1. But again, what if we're just sort of measuring people and we have to treat time as this continuous variate and we don't have balanced data? Well, how can we sort of still work with this? And that's where we can start to think about different ways of accommodating correlation patterns into our data. So what I'm going to do now is run through a bunch of different correlation patterns that we might think about using in these data. These are going to come up slightly throughout it, but more the idea is that if you can specify something, if there's a scientific reason for you to specify a particular pattern of correlation, well, then it can probably be accommodated by this method. It's an incredibly flexible method. And so I'm going to walk through the common examples, but there's going to be more that you might be able to come up with. And I'd encourage you to sort of think about that and think about the ramifications of specifying those. So currently we've assumed unstructured correlations. So we assume that the correlation between Yij and Yil is just rho JL, and we don't put any sort of restriction on that. Right? The problem with this is that it requires a load of parameters to estimate. And so what are some other ways that we could sort of simplify the number of parameters? Well, we could assume independence, right? It seems weird because we started this lecture by saying that the reason linear regression doesn't work is because of this lack of independence, but we could assume it if we didn't think that there was a strong reason to think that our outcomes were correlated over time. So in that case, we would just say that all of the row ij or row jl's are 0 as long as j is not equal to L, and that gives us independence, right? Now this independence is the exact same as just fitting a linear model, right? If you assume independence, you get the fit that we already performed in this case. It's almost never going to be appropriate to assume independence, but it is one way that we could simplify this example. We could also assume that the observations are exchangeable. Now, what we mean by this is that for any pair of observations, we're going to have the same correlation. So week 0 and week 1 have the same correlation as week 0 and week 4, same as 0 and 6, same as 1 and 4, 1 and 6, 4 and 6, etc. What this means is that we only need to estimate one correlation parameter, okay? We might also refer to this as the uniform or the compound symmetry assumption. So you're going to see exchangeable, uniform, compound symmetry. All of those mean the same thing. Now, this is a fairly strong assumption still, right? We only estimate one single correlation parameter. Now, it's a lot weaker of an assumption than making sure that they're all independent, but it's still quite restrictive. And so you'd want to really think scientifically, is there any reason to suspect that the correlations are going to be exactly the same? Because as a general rule, you would expect that, measurements that are closer in time to one another would have stronger correlations than measurements that are further in time, right? My blood pressure today is probably going to be more related to my blood pressure a week from now than it is my blood pressure 10 years from now, right? So we sort of think of these correlations as decreasing over time. But sometimes the exchangeable assumption is going to be valid. And when it's not, we can start to try and exploit other patterns that we might see. So if we want to take advantage of the fact that we see these correlations decreasing over time, then we might be able to assume this autoregressive structure. So what we're going to do there is we're going to say that the correlation is going to be given by some constant rho parameter, but we're going to raise it to the power of j minus L, right? And so the idea here is that rho is going to be a value that is between 0 and 1. And so if you raise it to higher and higher powers, the correlation becomes weaker and weaker. And so the further j is from L, the less the correlation is going to be between those. And that captures that natural decay that we were just talking about. Now, the problem with something like with all of the assumptions that we've made so far is that they still all are requiring balanced data, right? So even in this autoregressive structure, we're saying that we're subtracting these indices, but what if we're not measuring at the same time points? So you could think about generalizing this autoregressive structure slightly more, and instead maybe we would say that the correlation is going to be given by some function. Typically we're going to take the exponential function, that's why we're calling it an exponential structure here, but where, again, we have this rho parameter, but now we're multiplying it by the difference in time here. So once again, we're going to see that as Tj and Tl get further and further apart, we have smaller and smaller correlations, but now these t's can be sort of arbitrary, right? We just need the difference in time. And so this exponential structure is sort of a natural generalization of the autoregressive structure here. And actually you can prove, and maybe you'd be interested in doing this yourselves, that if you have balanced data, the exponential structure and the autoregressive structure are exactly the same. So this is just a way of accommodating non-balanced data inside of that autoregressive structure. So again, it can handle unequally spaced time points. And that's sort of a novel situation with it. We might also want to think of slightly different forms for the structure that we have there, right? So instead of just the difference, maybe we take the differences and we square them. And what that's going to do is decrease even faster the rate of decay of that correlation as you get further and further apart, right? So all of these different correlation patterns are going to sort of allow for us to capture different structures that we might expect to see in the data, and they're going to be more or less appropriate. Again, this unstructured assumption if you have balanced data, the unstructured assumption is always going to be able to be used, assuming that you have the computational capacity to actually estimate it. The problem with it is that it requires sort of far more parameter estimates. And so then from there, we have these varying other assumptions, which will be appropriate sometimes, won't be appropriate other times, but we sort of want to take the simplest model that's going to be appropriate to capture what's going on in our data. But in order to decide that, we're going to need to know scientifically sort of what is the rationale. Right, so that's one way of accomplishing data that aren't balanced, that are unequally spaced. It's also going to be a way of accommodating when we have very many time points, right? If the k times k minus 1 over 2 is going to be too large, these covariant correlation pattern matrices are going to help us with that. The last problem that we had is that we made the assumption that we have this constant variance. And so how might we be able to relax the constant variance assumption, right? We had assumed sigma squared for all different time points. So on the previous slide, we were looking at ways that we could replace this Ri matrix with a more parsimonious model. And so what we can do is we can actually start to think about taking, instead of a constant sigma squared, we can think about defining sort of arbitrary variance as well. So what we're doing here is we define this diagonal matrix, and along the diagonal, we just specify a different variance term for every different time point, right? So variance of yi1 through yiki, right? So for all of the different things. And if we write then sigma I as the square root of ai, and so that's just the square root of all of these different diagonal entries, times by the correlation matrix, times by the square root of ai once more, well, that's actually going to give us sort of an arbitrary correlation or covariance matrix, assuming that we have an arbitrary correlation matrix here. And so instead of factoring this out as sigma squared times by the correlation pattern, we could take this as ai square root times by the correlation times by ai again. And so that lets us relax that last assumption here, where now, again, we're estimating an additional, k minus 1 parameters here. But if we have the capacity to do that, well then formulating it in this way is going to let us do that. Okay. Now, there is just a piece of notation here. It's unlikely that we're going to correctly specify the correlation matrix. And so generally what we're going to do instead is we're going to write vi as that expression that we just had, which is going to be the square root of ai times by ri times the square root of ai. And we're going to call this the working covariance matrix. And the idea is that it's the one that we're working with. We're going to specify it as though it were true, even if it's not the same thing as the true sigma I. And from there, that's going to let us sort of do all of this estimation. So the punchline is that any correlation structure that you can imagine is going to be able to be used in theory within this method. And I'd encourage you to imagine some and play around with that. In practice, we're really only going to use a handful of them. They can be sort of made to be arbitrarily complex. You could think about making them depend on covariates other than just the time, for instance, right? We started to see some with that exponential model, say, that depended on specific time points. Well, you could do that with sort of all of the covariates. And we will see this in some R code. We won't so much look at it in theory because the expressions start to get quite complicated. But the idea is that you can take these ideas that we have here, you can specify your covariance structure to be whatever you want it to be, and then you could work through the maximum likelihood estimation again. And so, sort of as a result, this method that we were talking about of, treating univariate linear regression as our starting point, and then thinking of our outcomes as vectors, and then saying, what if we just assume that they're multivariate normal? Well, it turns out that this method is actually going to be able to accommodate sort of arbitrary amounts of flexibility in what we could envision. We're going to be able to answer lots of scientific questions using this. And So, it seems like it's sort of working out to be this incredibly flexible method. And so you might be asking, well, is this all we need? In this lecture video, did we just cover everything that we need for this course? Sadly, the answer is going to be no, and that's because there's still some limitations here. And so, we can talk about those now. The first big limitation is that this requires the complete specification of the mean model and of the covariance structure, right? So if we don't know what the true model for the mean is, or we don't know what the true covariance structure is, well, then it's not necessarily clear how we're going to be able to proceed with this method. And the problem is that in real data, you're almost never going to be able to correctly specify these things. If the covariance structure is misspecified, then inference regarding our beta hat is invalid. We do not correctly specify the covariance based on the maximum likelihood. This is not going to work. Our results so far have also assumed normality, right? So even if we manage to correctly specify the covariance and we correctly specify the mean, if the data aren't normal, we can't use what we've talked about so far because it has assumed normality and then looked at the maximum likelihood estimates. We also haven't handled nonlinear outcomes, right? We've only talked about continuous outcomes. And so what if instead we have binary indicators? This doesn't really help us with talking about outcomes that are anything other than continuous variables. So, these seem like fairly substantial limitations. And so what are we doing from here? What comes next? So despite these shortcomings, this serves as a very useful basis for analyzing continuous longitudinal data. In the next couple of lectures, what I'm going to do is talk about the same things here in theory and in application in our code, right? So we're going to go through the same concepts that we just went over, and we're going to review them from the theoretical lens, and we're going to review them from an applied lens. And so hopefully, between these 3 lectures, everything's going to become sort of crystal clear. So we're going to explore further how we can ask hypotheses or ask scientific questions in terms of statistical hypotheses. We're going to interpret parameters. We're going to build confidence intervals. We're going to see how does those asymptotic results actually come to be. And then what we're going to do is we're going to start to tackle the limitations that we just outlined. Right? So we're going to start to see how can we overcome those problems that we just specified. So in summary, we can't use linear regression to analyze continuous longitudinal data unless we're willing to assume independence. So instead, we assume multivariate normality, we get independence between the observations, and then we just impose a correlation structure on our data, and then we can use maximum likelihood estimation to get the parameter estimates. This gives us asymptotic results that we can use for inference and for hypothesis testing. And we can sort of be flexible about the correlation structures that we are using to allow for more parsimonious models to overcome issues that may have come up when we were sort of trying to fit the models with too many parameters. So that was probably a lot, right? We just covered sort of the core way that we're going to analyze continuous longitudinal data. If you have any questions about anything that we've talked about, please reach out to me at any point. But again, in the next 2 videos, what we're going to be doing is looking at this in more detail. So don't worry at all if you're not sure about where these theoretical results are coming from, or if you're not sure how you're going to be able to translate in practice, these ideas. The idea is to think about conceptually, what are we doing here? And then we're going to actually work through it. And so conceptually, what we've done is we've taken linear regression and we've said, yeah, but what if we're working with multivariate data? And, turns out that it's actually going to be quite an effective way of doing that. So I hope that all of this made a little bit of sense, and I will see you in the next video.